Welcome back, chemistry fans. We are going to start exploring our brand new, very short Unit 5. And this is going to be talking about redox reactions, which is a combination of two terms, reduction and oxidation. So let's jump right into it and let's see how we're going to deal with this new content. Okay, so we have these new term redox, although we talked about it briefly whenever we were balancing reactions. And so let's revisit what all those little terms mean. Today's focus is going to be about something called an oxidation state. It's going to have some synonyms, oxidation number or charge. But what you need to see in this first example here is that manganese in different compounds, it maintains, it has a different charge. Manganese oxide has a charge of +2. Manganese fluoride +3. Manganese oxide dioxide +4. Potassium permanganate. Why are all of these having different charges for manganese? It should just have the exact same charge. And the reasoning for this is the fact that it is such a large element in comparison to other elements. It is a transition metal, and it's complex in that it has many sublevels built into it, and it's willing to give up the electrons in those sublevels to achieve its stable octet in multiple fashions. So it'll give up its S's, its D's, and its P's and get itself to stable formations. What we ultimately want to use this information about oxidation states is to balance a reaction just like this. Looking at this one, you should start to see that there is a problem. The big problem we have is the fact that there's an oxygen on one side, but it's not over here on the product side. So that's going to lend itself to a very big issue. You can't just simply throw oxygens in there. We have to know where they are going to be and why they disappeared. And so we incrementally are going to work our way towards that. But how we start this process is by addressing something called the oxidation state, or the charges. We have to be able to predict those. Now, oxidation state, it's just the same as a charge. It's just saying that whatever these values are, it's more formalized, and it is assigned based on some calculations that we're going to do. Now, a charge is something that was predictable. Whenever we had ourselves a periodic table written upon the periodic table that we provided to that I provided to you at different times throughout the year, you had some predictable charges like elements in the first column +1, +2, +3, +4. And then -3, -2, -1, and 0. And sometimes this one also would be a -4 on top because the nonmetals were. And so that was kind of whenever we were just starting learning about these things. We just called them charges, and it made sense for us at the time. Now we're going to start to give it a more formal name. We're going to refer to it as an oxidation state. The process, or how it works, it means the same thing. If it's positive, it's losing electrons. If it's negative, it's gaining electrons. Now, want to remind you, this term oxidation means that it is losing electrons. So generally speaking, whenever we assign oxidation states, it means that we are centered on the nonmetals, the metals, and how they have lost electrons. However, we will expand that term and also assign negative charges. So they don't call it an oxidation state and a reduction state. They just give it one overall term, oxidation state. Oxidation means you lose electrons. Reduction means you gain electrons. Now, the difference between oxidation number and oxidation state. Oxidation number is the charge of the central atom. Oxidation state is the number of electrons that are lost or gained. Basically, they're saying the same piece of information. It's just a subtle difference between one or the other. Whenever I ask you the questions, it will always be in the terms of what is the charge, and then I will not call it by its official name. I'll just ask you, how did it achieve that how did it lose or gain electrons? So I will keep the two very confusing terms separate from one another. I will not try and make you know the difference between those. All right. So getting back to where we were with manganese having so many different charges, you could see here it has a +2, +3, +4, +6, and +7. Why? How do we know when it will have which charge? That is going to be our goal, and it starts with knowing these following rules. You're like, oh my gosh, how am I supposed to memorize these? Well, most of these are very commonsensical. If you're an element by yourself, you're not bonded with anybody, you're not exchanging electrons, then your charge is 0. That's rule number 1. That's simple. Rule number 2, if you are an ion that has a charge given to you, your charge is the ion, the charge that was given to you. So that also makes a lot of sense. Then it starts to now we start to get into some more detail. So the first two, very simple. Third rule says hydrogen is always +1. You already probably knew that because it's in the first column. So that makes sense. Nothing earth-shattering there. That is not a new piece of information. I'm going to skip rule 4 for just a second. I'm going to go to oxygen. It's always going to have a -2 charge. Always. So those are two very bedrock rules that we need to associate. And you're saying, well, how was I supposed to know that oxygen had a -2? Because we've already associated it on a periodic table. Hydrogen over here on the left is +1. Oxygen over here, it was a -2. That is written on a periodic table that you are given, and you're more than welcome to bring that out whenever the time comes appropriate for that one. Okay. Now, let's go back. There are certain times, however, that hydrogen will take on a -1, and that's whenever it bonds with a metal. And that's why it's odd, because metals are always positive. Hydrogen in the previous statement said it's always going to be +1. So this is not going to work out. They're both positives. So to compensate for that one, whenever we have a hydride, is what they're called, a metal bonded to hydrogen, its charge will take on a -2. There is also an exception for oxygens whenever it is O2 as a polyatomic ion. And you may ask yourself, well, how do we know when it's a polyatomic ion? Well, because the rules are going to be associated with the hydrogens, each having a +1 charge. That would be a +2. Well, then what's going to be the charge of each one of the oxygens? You said that they should be a -2. Well, that would mean that it's a -4. That +2 and -4 don't equal. That tells you then there's something else going on, and we have a peroxide where the charge of the oxygen is a -1. So that's a rule that you're going to have to pay attention to. It's tricky. It could pop up for you. Next, we have two simple rules. We already knew elements in group 1 and group 2. They have charges 1 and 2 respectively. We also knew that halogens have charges of -1. Now, here is the new piece of information that you really haven't thought of, but it made sense after we did crisscross applesauce. Whenever we had sodium and we had chlorine, we would crisscross applesauce, and they would balance out and they would write a formula. If I had magnesium and chlorine, a +2 and a -1, I could crisscross applesauce and I would end up with MgCl2. Well, the reality is what you didn't think of, whenever I have two of these chlorines, the overall charge is -2. Those total charges are going to equal 0. So that's what Rule 10 is saying. It's saying that all of these compounds, they got to always equal up to be 0. That's how you know if you've gotten it correct, is that all of your charges end up equaling 0. Thank you for the serenade, son. Rule number 11 is, though, if you have an ion, the sum of the charge is not going to be equal to 0. It would be equal to the charge of the polyatomic ion. So many of these rules make sense. The only things that are kind of new for you is that you have to pay attention to peroxide. However, it's already stated in rule number 11. And you also have to pay attention to hydrogens whenever they're in hydrides bonded with metals. They have a -1 charge. So those are two little rules, but everything else I think we are okay with. All right, let's move on. I wonder what he's playing. Who knows? So what are the charges? What are the oxidation numbers? What's the oxidation state? However you want to refer to this for these elements. Well, they're all elements that are in their normal state. So their charges, oxidation numbers, are all going to be equal to 0. All right, moving down. What if I have sodium and chlorine? Well, this is a +1, and chlorine is a -1. Now, why is that the case? Those look like 7s. They're +1s. Well, let's go and look at where they are on the periodic table. So sodium is over here. It falls into one of the rules that says that all elements in the first column have +1. All halogens fall into the rule that says they are going to have a -1 charge. So notice then the second rule that associates with, third rule that associates with this is that the sum of these two charges must equal 0. +1 - 1 equals 0. All right, we already worked a sample just like this one. Well, what are the charges of aluminum chlorine? Again, you could probably figure this out just by looking at your periodic table charges. Aluminum has a charge of +3, and chlorine we already established has a charge of -1. Well, we knew that if we've balanced out this formula here, but just to make certain that we're understanding, because they get more complex, the aluminum has a +3, and then there are 3 of the chlorines. That makes a sum of -3. Those two sums are going to be equal to 0. Now, what's the charge of this sulfur? And this is where it gets more complex. You're saying, oh, let's just look on the periodic table. That's not going to work anymore. This is where you have to start calculating. This is where things start to break down and become more complex. So here we have our sodium is a +1. We have a rule for that tells us what its charge is. We have a rule that talks about oxygen having a -2, but we have no rule about sulfur. So you can't assume what its charge is. You must now do a calculation of it. So what I look here and I see is that I have a total sum of +2 for both of the sodiums, and I have a sum of all the oxygens of -8. I know that all of this sum must equal to 0. So what is this value? 2 plus what? -8 equals 0. Well, if you look at this, you would say, oh, 2 plus 6, that would equal +8. And this is already a -8. So here is where we have some interesting scenarios. Sulfur is a +6. Look at your periodic table. What did you predict the sulfur to be? You would have predicted it to be a -2 right below the oxygen, but it's not. This is where you will have troubles if you make assumptions. There are no rules that talk about sulfur, so don't make them up. Follow the calculations to establish that. Let's go ahead and let's do a couple of practice. Barium is an element by itself. It has a charge of 0. Chlorine, it is an element in its natural state. It has a charge of 0. Phosphorus, it is an ion and it has a charge of -3. Strontium is an element and it has a charge, it's an ion that has a charge of +2. Now I have a rule about oxygen here, but I don't have a rule about uranium. So I know that the charge of each oxygen is -2. You may be saying to yourself, well, how do I know it's not peroxide? Because then we have no established rule on either side of this to help us through it. So it says always err on the side of caution and then assume that oxygens are -2. You have to have some indicator that this is a peroxide. You'd have to be given the name. You don't. So the sum here is -4, meaning that the sum for the oxygen for the uranium must be +4. Hydrogens always are +1s. It's not bonded to a metal, so it is going to have a +1 up here. The sum of 3 hydrogens is going to be +3, meaning that my charge on my nitrogen is -3. Now, because this is a polyatomic ion, in of itself, that tells me it's not a peroxide. So each of those oxygens are going to be -2. That is a sum of -4, meaning that this nitrogen is a +4. So had you just assumed that because on the periodic table it tells you it's a -3, you'd be wrong. On this chlorate, Each one of the oxygens is -2. That's a sum of -8. There's only one. Oh, sorry. I messed this up. It would be a +3 because +3 minus 4 is -1. The overall charge is -1. The same thing is true over here for my chlorine. It must equal -1. So the charge of this chlorine happens to be +7. So the overall rule, even though we had a rule that said fluorine and the halogens are generally -1, there is an overarching rule that says that oxygens and hydrogens always -2 and +1 respectively. So that's going to overrule any of the other rules. So now I have my charges for this one. All right, now my next one. I've got 6 oxygens. They're each -2. That is a sum of -12. I have a rule that says that bariums are in the second column, have a charge of +2. That's a charge of +4. So that means the difference is -12 + 4. I've got a difference of -8 for this one xenon. It always comes in 2s. This one's going to come in 3s. Very sorry. Sorry. All right. Oh, it's not. Ooh, sneeze. All right. We got one more to do. I don't know what my charge of dichromate is. I do. But let's say that we don't know that. We got to calculate this. Rubidium and sodium are both in the start of the periodic table in column 1. So that's a sum of +2, meaning that the overall charge of this whole entire chromate is a -2, dichromate, sorry, Cr2O7. So now I got to figure out what's the charge of my oxygens. Well, I know it's always -2. So that sum is -14, meaning I've got to make this thing equal -2. So that means the 2 chromiums must be +12, but there are 2 of them. So that means that each of the chromiums are going to be +6. This is what you must be able to do. You must be able to assign oxidation numbers, states, charges, whatever you want to call it. All right, next part. Once we are able to assign them, we must now predict which element has gone through oxidation, which element in a reaction has gone through reduction. So, as a reminder, oxidation loses electrons, reduction gains electrons. So, it's easy if I broke it up this way. You could see that the electron is on the right side. That means it lost an electron. If I see the electron on the left side, that's easy. It tells you you've gained an electron. So oxidation, lose, reduction, gain. Very easy. But what if it were written like this? You didn't have this piece of information. We'd have to individually analyze this cerium. It has gained an electron. You're saying, no, it hasn't gained. Yes, because electrons, remember, have a charge of -1. So 4 - 1 is +3. So the cerium gained an electron, whereas the iron +2, it lost an electron. And how do I know that? Because how do you get to +3 is that you have lost one more electron. You have to lose one more electron. So if I lose an electron over here, that would give me +2. And that's the reason why the electron appears on the right side. All right. Let's take a look at these. The oxidation numbers have already been assigned. We have to look at these and be able to see which one is becoming more negative. Now, I'm not saying that it's a negative value, but has moved towards the negative side. Well, the sulfur has gone from -2 to more positive +4. That is not becoming more negative. In fact, it's becoming more positive. So that one is easy to identify. If you're becoming more positive, that's oxidation. So the sulfur has gone through oxidation. Notice the hydrogens did not change. But notice that the oxygen on the left is 0, and over here on the right, it became a -2. That's becoming more negative. That means that it gained electrons. Let's do another example. So looking at my, let's take a look. The hydrogens on both sides are +1. They did not change. They're not going through any changes. My oxygens, They were at -2 and -2. They did not change. So they're out of the running. So let's take a look now. Did the chlorine become more positive? Yes. It moved towards the positive side. It wasn't negative. Now it's on the 0 side. So that is my oxidation. The element that was oxidized is chlorine. Manganese became more positive. Ooh. Sorry, became more negative. So the -4, it actually went closer to the negative. So that means it went through reduction. Oh, he missed a bad note there. All right. So now that we can establish who is oxidized and who is reduced, here's what we get to do. The element that goes through oxidation, the one that loses electrons, is called the reducing agent. So reducing agents go through oxidation. They are the elements that lose electrons. The elements that gain electrons, they are the elements that have gone through reduction. These are our last skills that we must be able to do. So I am hopeful that with a little bit more practice, do I have another example? I may have another example. Oh, I have another example. Let's do these and then we're done. So in the first one, it's 50-50. So let's take an assignment of their oxidation numbers. Oxygen is a 0 on the left because it's an element by itself. It's a -2 on the right. Well, now, because I've established it's becoming more negative, I know it's gone through reduction, meaning that this is my oxidation agent. Because there's only 2 of them, I know that this is my reducing agent, and it has gone through oxidation. All right, let's try the next one. There are 3 options, so this one's a little bit more challenging. We have a rule that says that sodium is always +1. So we know it is not going through oxidation or reduction. I look at the chlorine, it starts at 0 because it's an element by itself. The bromine ends with 0 because it's an element by itself. The chlorine ends with a -1. The bromine begins with a -1. So to go from 0 to -1 means you're becoming more negative. That's a reduction. You've gained an electron, meaning this is your oxidizing agent. The bromine has gone from -1 to a more positive 0. That means it went through oxidation, and this is my reducing agent. This is everything that I wish to share with you. These are the skills that you must maintain or produce or learn soon. Thank you so much for your time, and we will talk with you again soon. Farewell.